Hey, welcome back everybody. We are going to do a test for the quality of K population means, where K is like the number of population means, and the end result of everything we do is going to be to produce a picture like this. And this picture is very similar to these kinds of pictures we've already been doing, where we have a probability distribution there, we have some sort of a curve, and then we're going to be using the F table. That's the way I think about it. And so here's the F table. And I guess we'll just start by looking at this. And entries in the table give F alpha values. And so it'll give you like it's some F score or whatever you want to call it, F value, critical value. It's going to give you the probability from that point to the right. So the area under the curve from here to the right. And just so you could see how to use the F table, entries in the table give F alpha values, and alpha is your level. Alpha is your level of significance, and you can see that here, alpha 0.05 level of significance, and so, for example, with a 4 numerator degrees of freedom, and so here you have numerator degrees of freedom and 8 denominator degrees of freedom, and here you have denominator degrees of freedom, and a 0.05 area in the upper tail, so an alpha or a level of significance of 0.05, which means that by implication our confidence level or confidence coefficient would be 95%. And by the way, this example here in the textbook up top is not the one that's drawn out here, but you know, just to see like how do you get F 0.05 equal 3.84, we have to actually bring up this table here. And so here's this table, and I'm just going to make it bigger, and I'm just going to show you part of it. If I could find my mouse, there it is. So I'll just make this bigger, and let me see if I could bring this over. Let me just make this one bigger. Down here, grab it. There we go. That's bigger. And now I'm going to move it over. And so, you know, it's the same thing. You can see numerators up top, denominator on the left column. And so with that, we have here the numerator degrees of freedom are 2, and so we want, with numerator degrees of freedom 4, so we're going to bring that over. So here's the 4 column, and I'm just going to edge that onto the screen, so we're just looking at 4 right there. So there's our 4. So numerator degrees of freedom is 4, and denominator degrees of freedom are 8. And so here's 8 denominator degrees of freedom right there, and here's 4. Numerator degrees of freedom. So we're dealing with these numbers right here. And we have alpha, area and upper tail. We have an alpha of 10%, 0.1. We have 5%, 0.05. We have 2.5%, 0.025. And we have 1%, 0.01. And so at the alpha of 0.05 with 8 denominator degrees of freedom and 4 numerator degrees of freedom, 0.05, we're going to have 3.84, and there's 3.84. And so we're going to use that. We're going to use that to like get some points. We'll have some alpha, and that'll be our probability. Like from this point to the right, there's 5% of our data, which is why we have this arrow here going 5% of your data is from this point to the right. And so that's our p-value, 0.05. And then we're going to have a critical value associated with that. And the critical value will be that F value. So here that F value was with 8 denominator degrees of freedom and 4 numerator degrees of freedom, that F value is 3.84. For this problem here, we're going to have degrees of freedom in the numerator of 2. And so our numerator will be 2 right here, so there's 2. And we're going to have degrees of freedom in the denominator of 12, and you're going to learn all about what that means. And so here's our 12 denominator degrees of freedom. So we're going to be at 2 and 12. And we're going to be at 0.05 level of significance, 0.05 level of significance. So 12 denominator degrees of freedom and 2 numerator degrees of freedom at 0.05 will give us 3.89 as an F. And that gives us our critical value of 3.89 right there. Well, then we need to calculate our test statistic. And our test statistic, when we calculate that, and there's going to be a way to do that, and we're going to see that for testing for the quality of a K, where K is a like unlimited amount of population means greater than or equal to 3. But we're going to see how we calculate our F statistic, test statistic coming up. but we got a score, we will get a score of 9.18. And so if you look here, bump, 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 there is no 9.18 if you're at 10% or 5% or 2.5% or 1%, right? There is no 9.18. And so it's going to be between 0.01, 1%, and 0. So here our p-value becomes between 0.01 and 0. And so based upon this, we're in the reject area here, whether we're using the p-value approach or the critical value approach. And you can see that we're in the reject area, right? Because we're up here in this tail area. And so that's like stuff we've done before. So we would reject the null hypothesis. And by implication, the alternative hypothesis would not be rejected, which is another, that's how statisticians would say it, because they don't really speak English all that well. And and there's a reason for it. I'm just not deep enough into statistics to fully appreciate or understand why they say, and this we do not reject. The alternative hypothesis is how they say accept. So I was taking a little bit of a punch at them, but I felt like it was a little bit of a punch too far, so that's why I backpedaled a little bit there. Not all of the means are equal, so that's what, by implication, the alternative hypothesis is the one we accept, or as statisticians would say, we do not reject, which to me just makes me go, huh? All right, so that's the game plan. That's what we're going to end up creating. We've created stuff like that before, and I'm starting out kind of showing you things from the end to the beginning because there's a lot. There's a lot. Not going to lie to you. There's like a whole bunch of new stuff to wrap your head around and synthesize. But we're going to get there. I have a game plan, or a game plan is unfolding, and I'm just riding that wave. And I'm trusting. Here you go. I'm going to get metaphysical on you. And here's an ontological perspective. And you can look up what that means if somebody gets metaphysical on you. Metaphysics, define, is the branch of philosophy that deals with the first principles of things, including abstract concepts such as being, knowing, substance, cause, identity, time, and space. You can pause the video and read about it. I love it. It's one of my favorite words. And ontology is the branch of metaphysics that deals with the nature of being. So metaphysics here. I believe that there are benevolent forces in the universe, which, I think of as like both benevolent forces in the universe and my benevolent ancestors, and they guide us and they lead us. At least they guide me and they lead me. That's how I think about it. But I also think about it like they guide us and lead all of us. And anyhow, I don't really subscribe to any one religion, but I believe that, there's many different ways to talk about the benevolent forces in the universe. That's my perspective. All right, so I think that there's benevolent forces guiding us, and there's a lot of color here, a lot of information. We're gonna do this problem here, and so, if this is the end result, here's the problem. And the problem was that there's this company, Chemitech, developed a new filtration system for this is the example, for municipal water supplies. There are different methods that can be used to assemble the system. Chemitech has narrowed it down to 3 methods, A, B, and C. Chemitech wants to determine which assembly method can produce the greatest number of filtration systems per week, right? If you do assembly method A or assembly method B or assembly method C, does it make a difference, right? Does it make a difference? Are the different assembly methods all equal to each other? Or is there one assembly method that is better than the rest and they're not all equal to each other? And one assembly method here, A, B, or C, is going to produce more units every week. So to test this, they select 15 workers and then randomly assign 3 treatments to 5 of the workers. And so down here you have 5 workers, and then you have here in the columns you have treatment A, B, and C. And here's what worker 1, right? Like I don't know if these are minutes or days or years. Trying to keep it a little bit light. That are being used to measure. I would say these are probably minutes. How many minutes did it take to assemble using these different methods? And so each worker will do each method, right? They'll try method A, method B, method C, and then we'll get all those times for each worker for method A, all those times for each worker for method B, all those times for each worker for method C. We'll calculate the mean for each of those methods. So 52 here is looking good. And then we'll calculate the sample variance for each of those methods. And so here you can see the variance. This one had a little bit more variance. That's interesting. And then we'll calculate the sample standard deviation. And so there's the sample standard deviation for each of those methods. So this is the most consistent method right here, the least variability. And but it has the highest mean time. And then this one is like still pretty consistent, right? Not too variable, but it's 62, and that's still like 10 minutes higher than 52. And so we might need to figure out if there's an outlier here, like if we were just like looking at this, like but even that outlier is still a pretty quick time. So I would say that, method C is going to win. And when we look at this, and that's just like looking at the data. That's just looking at the data. Like, let's just look at the data and intuitively try to make sense of it. And we could see that this one, right, had more variability. But maybe it's not too significant. 47, the range here is 47 to 59. So we might calculate our range just to kind of compare the range of variability on that. The range, so that was 47, 59 is 12. And then the range here, we have 58 to 71, which is 13. And then the range here is 58 to 67, which is 9. So the range here is 13, the range here is 9, the range here is 12. So I'm not going to be too concerned. Like if I was in the real world and not in academia, I would just say, you know what, we're saving 10 minutes every unit, and that's a lot. And so this is the way we're going to do it. And really the range tells me that this isn't too bad. That's the way I'd just be thinking about it. And I'm sharing that with you so that you're getting an idea, a sense of how you actually apply statistics in the real world and to help you make decisions. And so, when we calculate all that, we get way up here where we have to reject, like way up here where we have to reject, like our critical value is 3.89, our test statistics 9.18. We're looking at 5% or less of our data, and we're less than 1% of our data, right, from this point to the right. And so we reject the null hypothesis. I forgot to write that on here. We reject the null hypothesis. And that means that by implication, this is the one we accept, that not all of the means are equal, and that there is a better way to do this. And notice that, from this, right, we're able to intuitively look at the data, but the test that we're going to use here is analysis of variance, And so that's also referred to as ANOVA. And it's a randomized design because randomly, right, we chose 15 people and then we selected 5 workers and assigned the treatments. Like randomly, we assigned treatments to 5 workers. So just randomly did that. And so that makes it random. And I'm going to stop this video here because we're at 12 minutes. And then in the next video, we're going to dive into this and just look at it in more depth and go on to the next steps. And start to learn some terminology and some of the formulas that we need to know to do all these calculations. So that's what's coming. See you in the next videos.